This video is on the objective, compute the value of the test statistic, which will be a z-score, or a z-value in this case, for a hypothesis test for one population mean with a known standard deviation. Alright, so this is video number 2 on this objective, so hopefully you've seen number 1. I'm going to take a little less time explaining things in this one and just kind of go through it. So this is through another problem related to that objective in your Newton Alta homework. All right, and here it is. So again, if you're unfamiliar with it or you want to see more, click on More Instruction. Look at their videos, their notes, their examples. Hopefully that helps you. All right, here. Suppose a chef claims that her meatball weight is less than 4 ounces on average. Several of her customers do not believe her, so the chef decides to do a hypothesis test at a 10% significance level in order to persuade them. So she cooks 14 meatballs. The mean weight of that sample of 14 meatballs is 3.7 ounces. Now the chef knows from experience that the standard deviation for all her meatball weights is half an ounce, 0.5 ounces. Alright, so this time, I'm not going to take you through those first steps. They give us, first of all, we have a claim. Let's suppose, let's say mu, right, mu represents the average weight of all this chef's meatballs, right, the entire population. The claim is that mu is less than 4 ounces. Mu is less than 4. And that would be the alternative hypothesis. Remember, the alternative involves no equality. So mu is less than 4. And if it's mu is less than 4, that means we're performing a left-tailed test. Right? It's something to keep track of. And then the null hypothesis always involves equality. So it would be that mu is greater than or equal to 4, right, which is the opposite of this. But what we're going to be assuming is that mu equals 4. Alright, so this here, mu equals 4, we're going to assume that that is, the population mean, that is the mean weight of all this chef's meatballs. Then the second step would have been to identify a significance level, which was mentioned here at 10%. So alpha is 0.1. If it's not mentioned, we're going to assume that it's 5%, but here it is mentioned as 10%. All right, then they're asking, what is the test statistic, right, the z-score of this one mean hypothesis test rounded to 2 decimal places? All right, so I'll pull up a piece of paper here, and now let's take a look at our sample. All right, let's get rid of the calculator for now. So, we had a claim, set up hypotheses, found, stated the significance level. Now we're looking at a sample and calculating a test statistic for our sample. Now the size of the sample was 14, right? It says she cooks 14 meatballs. And the mean weight of this sample, right? So the x bar, the average for a sample, the sample mean weight was 3.7 ounces. Now, remember, from the null hypothesis, we're going to be assuming that the population mean, the mean weight of all her meatballs, is 4 ounces, is equal to 4. And then something else that is known is that the population standard deviation, because it said in that last sentence, the chef knows from experience that the standard deviation for her meatball weight is half an ounce. So this is known, right? And if sigma is known, then we know the following. Remember, by the central limit theorem, for means, the distribution of x bars, right? And this is assuming, of course, we have a normal distribution to begin with, but remember the distribution of the x bars of all the sample means for samples of size 14 would be approximately a normal distribution with a mean of mu sub x bar and a standard deviation of sigma x bar, where mu x bar, right, the mean of the means, remember, was the mean of the population. And from the null hypothesis, we have assumed that this mean is equal to 4. Right, this is coming from the null hypothesis assumption. And the standard deviation of the means, remember, is the standard deviation of the population divided by the square root of the sample size. So that's 0.5 divided by the square root of 14, right, which I'll punch in and round. I mean, we'll use the whole thing, but let's take 0.5 divided by the square root of 14. And so that's approximately 0.134 ounces. And I'll draw a little picture. We have here's a number line with representing possible values of the sample means for samples of size 14. We're saying that this is normally distributed. Right? It's a nice symmetrical bell-shaped curve over that. Normally distributed, where the mean, right, underneath the peak here is 4 ounces. Right? What's being assumed from the null hypothesis. And with a standard deviation of about 0.134. So under these remember these inflection points should be about one standard deviation away above and below. So this value here, that's one standard deviation above, is 4.134, and this value here, that's one standard deviation below, is about 3.866. About, I remember that, and this is a normal curve, so about 68% of the data of the area is between these two, whatever. All right. What we're trying to do, though, is figure out where does our sample mean fall. All right, there's our sample mean. She cooked these 14 meatballs, and the sample mean was 3.7 ounces. Where does that fall on this number line here? Well, that's over here somewhere. 3.7. That's our sample mean, or her sample mean. All right, and then the question becomes, what's the z-score, right? This is a normal distribution, so when we talk about how many standard deviations away from the mean is it, that's a z-score. And that's what our test statistic is. So z-test. All right, I'll say the z-score, our test statistic, is just the z-score of 3.7 in this distribution. So I take the value 3.7, and I figure out how far away from the mean is that. Right? So I subtract 4. And then how many standard deviations is that? I divide by the standard deviation, which was this 0.5 divided by the square root of 14. And then they're asking us to round this to 2 decimal places. All right, and then if I wanted, I could draw another picture where we're looking at z's, where we're looking at z-scores, the standard normal, but I'm not going to do that this time. All right, let's just find this. Now, in the numerator, I'll put this in parentheses, right? Well, come on. 3.7 minus 4 is negative 0.3, right? So there's the numerator. And then divided by my previous answer, right? My previous answer was the standard deviation, that 0.5 divided by the square root of 14. So we're getting a z-score of negative 2 points to 2 decimal places. That's 2.4. All right, so this tells me that our sample has a mean value that is 2.24 standard deviations below the mean. And again, that's pretty far away. Usually if you're more than 2 standard deviations away from the mean, that means your value is pretty far from the middle. pretty far from the mean. So what we're going to do later, again with the critical value method or the p-value approach, we're going to make a decision. Is this far enough away from the middle to where I'm going to reject the null, right? Because remember, the null hypothesis was you're assuming that the mean value is 4. So you'd think if the mean value is 4, then our samples, any sample we take, should be really close to it, right? It should be reasonably close to it. This one is not that close. I mean, it's not that far away either, but it's still more than 2 standard deviations away. So if that's the case, on our first sample, then we probably won't like having, we probably would say that this assumption is bad. Maybe the mean is not 4. If our first sample came in at, over 2 standard deviations away from 4. So that's what we're going to do after this. But for right now, we're just developing, finding this test statistic. So it's negative 2.24 when rounded to 2 decimal places, and that's all they're asking for. And again, hooray, read the answer explanations, right? They go through the same exact calculation I went through down here. And read the answer explanations whether you're right or wrong. When you're right, you can see that your reasoning was right. Make sure it was. And if you're incorrect, of course, read it. Because maybe you can figure out where you went wrong, and then the next time you see a problem like that, you can do better. All right. So hopefully these couple videos on this objective help you when you're working on problems related to this objective. And thank you very much for watching.